All right, let's get moving. Good morning. Today we have, if everything works out, we have some fun for you guys. I hope it works out, so we'll see. So what I'm going to do today is a very major application of the frequency response and the frequency domain analysis of circuits. And this application area is called filters. The area of filters oftentimes demands a full course or a couple of full courses all by itself. And filters are incredibly useful. They're used in virtually every electronic device in some form or another. Okay, they're used in radio tuners. We'll show you a demo of that today. They're also used in your cell phones. Every single cell phone has a set of filters. So how do you pick, for example, how do you pick a conversation? You pick a conversation by picking a certain frequency and grabbing data from there. They're also in wide area network wireless transmitters. So do we have an access point here? I don't see one, but so you've seen wireless access points. Again, they work. They have filters in them. So virtually every single electronic device contains a filter at some point or another. And so today we will look at this major application of frequency domain analysis. So before we get into that, I'd like to do a bit of review. Okay? So the readings for today correspond to chapter 14.4.2, 14.5, and 15.2 in the course notes. All right, let's start with the review. So we looked at this circuit on last Friday. Okay, but I said that for our analysis, we're going to focus on this small region of the playground. And what's special about this region of our playground is that I'm going to focus on sinusoidal inputs. Okay? And second, I'm going to focus on the steady state response. Okay, how does the response look like if I wait a long time? And then we said the time domain, the full-blown time domain analysis was hard. This was remember the agonizing approach. And then I taught you the impedance approach in the last lecture, which was blindingly simple. Okay? And in that impedance approach, what we said we'd do is, and I'll apply the approach right now, and in seconds derive the result for you. But the basic idea was, we said, what we're going to do is assume that we're going to apply inputs of the form Vi e to the j omega t. Okay, so wherever you see a capital and a small, there is an implicit e to the j omega t next to it. Okay, I'm not showing you that. Okay, and what I showed last time was that, and the class before that was, once you find out the amplitude, once you find out the multiplier that multiplies e to the j omega t, it's a complex number, you have all the information you need. Okay? And once you have this, you can find out the time domain response by simply taking the modulus of that for the amplitude and the phase of that to get the angle. Okay? And that gives you the time domain response. So our focus has been on these quantities. So the impedance method says what I'm going to do is replace each of these by impedances. And the corresponding impedance model looks like this. So instead of R, I replace that with ZR. And instead of the capacitor, I'm going to replace that with ZC. And this is my VC. ZR is simply R. And ZC was going to be 1 divided by SC, where S was simply a shorthand notation for j omega. So based on this, once I converted all my elements into impedances, then I can go ahead and apply all the good old linear analysis techniques. I will discuss a bunch of them today. So as an example, I could analyze this using my simple voltage divider relationship. So VC is simply ZC divided by ZC plus ZR times VI. Okay? And that in turn is, well, let's say I divide this by VI so I can get the response relation, is ZC divided by ZC plus ZR. And ZC I know to be 1 by j omega C plus R. Okay? And multiplying throughout by j omega C, I get 1 divided by 1 plus j omega C R. Okay, it's incredibly simple. And so this is simply the, that's called the frequency response. And it's a transfer function representing the relationship between the output complex amplitude with the input. We can also plot this as, so notice that in our entire analysis, we have not only assumed sinusoidal input, but we're also saying that let us look at this only in the steady state. Okay, so we're going to wait for time to be really, really large and then look at the response. And so therefore, we were going to plot the response not as a function of time, okay, but rather we're going to plot the response as a function of omega. Okay, so what we're going to say is that I'm going to input a sinusoid, okay, and my output's going to be some other sinusoid. And since I'm waiting for a long time to look at the output, time doesn't make sense anymore. Rather, my free variable is going to be my frequency. So I'm going to change the frequency of the input that I apply, and so I'm going to plot this as a function of omega. So this represents a completely complementary view of circuits. The time domain view, and then there is a frequency domain view. The frequency domain view says, how does this circuit behave as I apply sinusoids of differing frequencies? Okay, so I can plot that relationship in a graph like this, and this relationship is simply given by a parameter h, the transfer function. It's a function of omega. And I can also plot the absolute value of that. And let's take a look at what it looks like. So I can look at functions like this and very quickly plot the response. Okay? I'm going to do a whole bunch of plots just by staring at circuits and staring at expressions like this. And you'll see a number of them today. So first of all, the way you plot these is look for the values when omega is very small and when omega is very large. Okay? So when omega is very, very small, this term goes away. And so for very small values of omega, the output is simply 1. VC by VI is simply 1. This part goes away. What happens when omega is very, very large? When omega is really large, this part dominates, is much greater than 1. Okay? So if I ignore 1 in relation to this guy and take the absolute value of that, then I simply get 1 divided by omega CR when omega is very large. So when omega is very large, I get a decay of the form 1 over omega CR. So I know the value for small omega, and it looks like this for very large omega. And if you plot it out, this is how it is going to look like. So this form, let's stare at this form for a little while longer. Okay? And let's plot some properties of it. First of all, you notice something else. When omega CR equals 1, when omega CR equals 1, then, in other words, when omega equals 1 by RC, notice that the output is given by 1 plus J. Okay? And the absolute value of that is simply 1 divided by square root of 2. So, in other words, when omega is 1 by RC, okay, when omega is 1 by CR, then the output is 1 by square root 2 times its value when omega is very, very small. So that's one little piece of information. And if you look at the form of this, I'd like you to stare at it for a few minutes and try to understand what this represents. Okay, so this says that for very low frequencies, the response is virtually the same as the input in amplitude. In other words, if I apply some very low frequency sinusoid of some amplitude, then the output amplitude is going to be the same as that amplitude. Okay, and that's a 1. Now, it also says when I apply a very high frequency, at very high frequencies, it decays. Okay, so this graph, which says that I'm going to pass low frequencies without any attenuation, without hammering it, but I'm going to clobber high frequencies. Okay, I'm going to clobber high frequencies and give you a very low amplitude signal at the output, but pass through almost without attenuation the input at low frequencies. Okay, and so this is an example of what is called a low pass filter, or LPF. Okay, what this is saying is that this little circuit here acts like a low-pass filter. That it's a low-pass filter because it passes low frequencies without attenuation, but kills high frequencies. Okay, so if I take some music, and you will do this, you will do experiments with this in lab 3. When's lab 3? People are doing lab 3 right now, right? So lab 3 is going on right now, and early next week as well. And in lab 3, you will play with looking at the response to music of different types of filters. So if I apply some music here, you will see that the output will pass low frequencies, but really attenuate high frequencies. So you'll hear a lot of the low-sounding bass and so on, but attenuate a lot of the high frequencies. All right. The other thing that I encourage you to do is WebSim has built-in pages for a large number of such circuits. So you can go in there and play with the values of RC, or L for that matter, for a variety of circuits. And if you click on frequency response, you actually get this, you get both the amplitude response and the phase as well. Okay, so you can play with various values of RLC and see how the frequency response looks like for each of those circuits. Okay. As a next step, what I'd like to do is just give you a sense of how impedances combine. Okay, this is not, this won't be very surprising given that they behave just like resistors, but it's good to go through it nonetheless. So suppose, just to build some insight, suppose I had two resistors in series, all right? R1 and R2, and this was my A and B terminals respectively. And let's say the complex amplitude of the was VAB across this. Then I can relate, and let's say IAB was the current. I can relate these resistances, or I can relate VAB and VAB and IAB as follows. Simply VAB divided by IAB equals R1 plus R2. Okay, I know that. And the same thing applies to R viewed as an impedance. It's still impedance is R, and so this one still goes ahead and applies. The second thing I can try is a circuit of this form, A, B, and I have an R and an L in R1 and an L in this case. And what I can do is, in the impedance model, I can view this as a impedance of value j omega L. Okay? And I can also combine them to get the impedance between A and B. Okay, much as I got a resistance between A and B, I can get an impedance between A and B as VAB divided by IAB, and that will be given by ZR1 plus ZL, and that is simply R1 plus J omega L. Similarly, I can do an even more complicated circuit. So resistance, and here I have a capacitor in series with a resistance, and then I apply inductor to it. So this is A, B, IAB, and plus minus VAB. And let me call this R1, and let me call this R2, and this is C and L. So I can go about combining these in much the same manner that I combined my resistances in the series parallel simplifications. So I can define an impedance ZAB between the A and B terminals as ZR1, okay, plus Z of this combination, impedance of this combination, which is simply impedance of C and that of R2 in parallel with each other. So I get ZC in parallel with ZR2. Notice that this notation simply says that look at the impedance of the capacitor in parallel with a resistor. And then finally, I add to that the series impedance of the inductor, ZL. Okay, exactly as you would have done for resistances. If all of these were resistances, you would have said R of this piece plus the R of the parallel combination plus the R of whatever was here. This time around we have impedances. And replacing this with the values, this is R1. Okay? I know for ZL, it's J omega L. And so for ZL parallel ZR2, it is given by ZC, ZR2 divided by ZC plus ZR2. Okay, which is simply R1 here and J omega L. And let me just substitute the values here. So I know that ZR2 is simply R2. ZC is 1 by J omega C, and then 1 by J omega C plus R2. And I can go ahead and simplify that further and get my impedance ZAB. So notice how simple our analysis has become. Okay, using this technique, we've managed, using the impedance method, we've managed to convert our analysis from solving differential equations to going back to algebra. Okay, so a large part of what we do in circuits is see how we can get back to really simple algebra and try to be clever about how we do things. Okay, so this is as far as analysis is concerned. In the next 5 minutes, I want to give you some insight into how you can build different kinds of impedances. Okay, and I won't go into too much detail, but give you some insight into how you can get a sense for the kind of filters you want to design, or at the very least, given a filter, how can you very quickly get some insight into what kind of filter it is, how it performs, what its frequency response is, and so on. And this time around, this piece of intuition will be in honor of humans. And back to a Bend It Like Beckham series, I call this Unleash It Like Humans. Okay? So, so what experts in the field do is they don't go about sitting around writing differential equations, but rather use a lot of insight into how they solve these things. And so in honor of humans, I'll label this Unleash It Like Humans. So let's get some insight into how the response of various elements look like. So let's take, for example, I have some impedance Z. Okay? Let's say this could be a resistor. It could be a resistor. It could be an inductor. Or it could be a capacitor. Okay, let's take a look at what the frequency response of just these elements look like. In other words, what is the frequency dependence of Z itself Okay, let me just plot the impedance of each of these elements as a function of frequency. Okay, let me just take the absolute value of that impedance. Notice that it's a complex number. For the inductor, it's j omega L. And let me take the absolute value, omega L in that case, and plot it for you. And use that to develop some insight. So let's do a simple case first. If Z is a resistance of value R, then no matter what the frequency, my value is going to be R. If I have an inductor of value L, then the impedance is going to look like j omega L. And so I'm going to get omega L for that. And the dependence of that simply says that for low omega, the impedance is very small. For omega 0, the impedance is 0. And it increases linearly with omega. Okay, so it's omega L for the inductor. Impedance increases linearly as I increase the frequency. What about for the capacitor? For the capacitor, the impedance is 1 divided by j omega c. Okay? And so therefore, I get the dependence being related to omega c, which says that for very high frequencies, the impedance is very low. But for very low frequencies, the impedance is very high, and I get a behavior pattern that looks something like this. It goes as omega c. I'm sorry, 1 by omega c. Okay? So as omega is very large, my impedance is very small. Omega is very small, my impedance goes towards that of an open circuit. Now, this is not surprising. You've known this before, right? That a capacitor behaves like an open circuit for DC. An inductor behaves like a short circuit for DC. Notice that the 0 frequency here corresponds to DC. So the capacitor looks like an open circuit for DC, very high impedance. Inductor looks like a short circuit for DC, very low impedance. And the opposite is true at very high frequencies, while R is a constant throughout. So let's use this to build some insight into how our circuits might look. So let me do this example. So let's say I have a VI, and I measure the response across the resistor. So I measure VR divided by VI, okay, and take the absolute value and take a look at how it's going to look like. So I want you to stare at this for me and help me with what the response is going to look like. So let's take incredibly high frequencies. At very high frequencies, okay, this has a very high frequency. What does the capacitor look like to very high frequencies? Is it an open or is it a short? The short circuit. Okay? So at very high frequencies, if the capacitor looks like a short circuit, then VI simply appears across the resistor, which means that at very high frequencies, the output is very close to the input. At very low frequencies, what happens? At very low frequencies, the capacitor looks like an open circuit. So if this looks like an open circuit, then very little voltage will drop across this resistor here because most of it is going to drop across the capacitor. So what's going to happen is for very low values, I'm going to be looking at something out here. Okay, and because of that, my response looks like this. Okay, and this is of a different form than the one you saw earlier. In this case, I pass high frequencies, but attenuate low frequencies. Not surprisingly, this is called a high-pass filter. Okay, you need to begin to be able to think about capacitors and inductors in terms of their high and low frequency properties. And if you get that, if you develop that intuition, once you develop the intuition about capacitors and inductors and their frequency relationship, that will be a big step forward in 002. Okay? If you get that insight, you will go a long way in terms of knowing how to tackle problems and being able to quickly sketch responses. Yes?
Problem
Okay. So in the case of, if you get something like j omega L, right, what you can do is take the limit as omega goes to 0. And if it's omega L, then notice that it's going to start linear. Okay? And on the other hand, when you get very high frequencies, for example, if you get 1 by something omega c, then this is a hyperbolic relationship, so it's going to go ahead looking like this. So you can take a look at a lot of these functions at their very low values and see how they look like at that point. Okay? All right. So the next one I'd like to draw for you is something that looks like this. So let's say, for example, I have a inductor L and a resistor R, and I want to see what that looks like. So in this particular example, I have h of take the absolute value. So what's this going to look like? I'm going to look at the value across the resistor here. So here what I'm going to find is that at very low frequencies, okay, this guy is a short circuit. Okay, since this guy is a short circuit, all the voltage drops across the resistor, so it's going to look like this. And at very high frequencies, what I'm going to find is that the inductor is going to appear like an open circuit. And so therefore, all the voltage is going to pretty much drop across the inductor. Okay, so it will be R divided by something plus omega L. So at high frequencies, this guy is going to taper off to 0. And so it's going to look like this. And this is back to my low-pass filter. Okay? Just to go back to a question asked earlier, is how do you know what this looks like? So I can very quickly write down the expression for h of j omega. This is simply going to be R divided by R plus, if this is VR. VR is simply R divided by 1 plus j omega c. Okay? If I multiply it out by j omega c in the numerator and the denominator, I'm going to find j omega c here, and I'm going to get 1 by j omega c here. Okay? And what's going to happen with something like this is that as omega becomes very small, then I'm going to ignore this. Okay, when omega becomes very small, I can ignore this with respect to 1. Okay, and I get R j omega c. So given that, is what I've drawn here correct or wrong? So if this goes away with respect to 1, I'm left with R j omega c, right, for very low frequencies. So given what I've drawn here, is that correct or is that wrong? Well, it's hard to say. For very, very low frequencies, it starts out being linear, right? Because it's a omega relationship, right? And then it goes up like this, and then goes out there. Okay. Let me go on to the next, another example. Okay, let me do another example here, which is something like, I need to make sure I don't make a mistake here. So if I get Rj omega c by Rj omega c, and you know what? This is ends up being a first order system, and so it's going to look like this. Okay, I blew it there. Okay, so back to this system here. If I have an L and an R, and I look at this equation to look at what happens across L, you can plot that again. And for very low frequencies, it's going to be 0 amplitude here. And for very high frequencies, this is going to be an open circuit. And so the response is going to look like something like this. Okay, that's going to end up being a high pass filter. Okay. So as another example, I'd like to do a series RLC circuit. Okay, and try to get you some sense of what that output looks like. So let's use our intuition and first write down what this looks like, and then go and do some math and see if the math corresponds to what our intuition tells us. So I want to plot VR with respect to VI, and I want to plot it there. Okay, so for something like this, what happens at very low frequencies? Okay, we're just looking to get a very crude shape, very crudely, what this graph is going to look like. Okay, very, very crudely, what this graph is going to look like. So given that I'm taking the voltage across VR, what happens at very low frequencies? At incredibly low frequencies, the inductor looks like a short circuit. Okay, but the capacitor looks like an open circuit. Okay, it's an open circuit in series with a short circuit, ends up looking like an open circuit. And so therefore, all my voltage falls across VR. Okay, all my voltage falls across VR. Now, what happens at very high frequencies? At very high frequencies, the capacitor looks like a short. But the inductor looks like an open circuit now for very high frequencies, correct? Just remember, capacitor short for high frequencies, inductor open for high frequencies. So this ends up having a very high impedance. So at very high frequencies, this guy has a very high impedance. Okay? And because of that, I end up getting, so for a high value of frequency, I end up going in that manner. So this behavior has the effect of the capacitor here, and for very high frequencies, I get the effect of the inductor. Okay? And then, so this means that I have very low values for low frequencies, very low values for high frequencies. Okay? And as the frequency increases, I do something like this. Okay, so I keep building up, and then the inductor begins to play a role, and then I taper off again. So this kind of a filter, where I kill low and high frequencies and pass intermediate frequencies, is called a band pass filter. A band pass filter. This means that it passes frequencies in some band. Let's get some more insight on this by writing down the equations. So VR divided by VI is simply R, using the impedance relations. It's R, and divided by j omega L plus 1 divided by j omega C plus R. Okay? I'm going to use this equation later, so let me stash it away on my stack and put a little notation there. So I'm going to multiply throughout by j omega C, and what I end up getting is j omega RC divided by 1 plus R j omega RC. And then here I get j times j is minus 1, so I get minus omega squared. Let me rewrite this way. So I get minus omega squared. So jj is minus 1. Omega times omega is omega squared. And then I get an LC. Okay? That's what I end up getting. And if I take the absolute value here, I end up getting, back to your complex algebra, I get a square root of this real value squared plus imaginary value squared. So 1 minus omega squared LC, okay, plus omega RC squared. Okay, this is from, you can look it up in your complex algebra appendix in the course notes. Okay, it's simply omega RC here, and then square of the real value plus the square of the imaginary value, and take the square root of that. Okay. So by staring at this, you can notice that you realize a really important property. When omega equals LC, when omega equals 1 divided by LC, what happens? When square root of LC. When omega is 1 divided by square root of LC, okay, then omega squared times LC becomes 1. Okay, when this is true, then this becomes 1, and 1 and 1 cancel out. Okay? And not only that, when these cancel out, these two cancel out as well at that point. So I end up getting a 1. So which means that when omega equals omega naught equals 1 by square root of LC, okay, I end up getting a value that is 1. This is pretty amazing, which means that if I drive this at omega naught, okay, if my sinusoid here has a frequency omega naught, where omega naught is 1 by square root of LC. So if I'm sitting here, okay, and this is a black box on the right-hand side, and I drive this at a frequency omega naught equals 1 divided by square root of LC, what does this entire circuit look like to me? So I'm sitting there, the black box here, I'm driving it at omega naught equals 1 by square root of LC at that frequency. What does that circuit look like? Yes? It looks like a resistor. Okay, it's pretty amazing. It means that even though I have an L and a C here, if I happen to drive this at omega naught, then the circuit looks purely resistive, and it seems to have give me the same input appearing at the output. In other words, the effect of these two cancels out. Okay, and that aspect is called driving the circuit at its resonance point. Okay, resonance is when you're driving the circuit at omega naught equals 1 by square root of LC. So I'll very quickly sketch for you a couple of other ways of looking at circuits. So supposing I looked at this value here at VLC. If I looked at the value across the inductor and the capacitor, okay? What will the frequency response look like? Like I'm looking at the voltage across the inductor and the capacitor in series. Let's see. Let's go back to our usual mantra, okay? Think about Steve Human when you do this. What would he do? Okay, he would say, aha, at very low frequencies, the capacitor is going to look like an open circuit. Okay, so in my voltage divider, I'm measuring the voltage across an open circuit, so the entire VI must drop across the inductor capacitor. Similarly, at very high frequencies, the inductor looks like an open circuit now. Okay, so it looks like this. So at very high frequencies, inductor is an open circuit. And so I get, again, I'm looking at the voltage divider across the near infinite impedance. Okay, so I get a high value here as well. Well, and in the middle, the value dips. And I get something like this. Okay, so this thing is called a band stop filter. Okay, so here I can nail any specific frequency as long as the frequency falls in roughly that regime. Yet another example. The reason I'm working out so many examples is that to experts, a large part of what they do is look at a circuit and boom, give a rough form of how it looks like. Okay, that can get you, half the way there in most of what you're going to do. So how does this look like? So if I take the voltage V naught versus VI. Well, let's take a look. At very low frequencies, the inductor looks like a short circuit, correct? So I'm taking the voltage across a short circuit, so it looks like this. At very high frequencies, I'm taking a voltage across a parallel combination, but the capacitor is now a short circuit. So that looks like a capacitor. So this looks like an inductor out here, And this is the capacitor taking, holding sway here. And so somewhere in the middle, it goes up and comes down like that. So it's a bandpass filter. So but what's amazing is that you can take fairly complicated circuits, and just by doing a quick analysis of what happens at very low frequencies, what happens at very high frequencies, you can roughly sketch the response. And then what you should do in addition to that is, if it's a second order circuit, just assume that it's going to do something interesting at its resonance frequency, at omega naught equals 1 by square root of LC. Something interesting is going to happen. Check it out. Okay? And for circuits that are first order, RC or RL, the important number is the time constant RC. Okay, usually when you're driving it at 1 by RC, omega equals 1 by RC, then what happens is that you oftentimes end up getting a value that is 1 by square root 2 times the input value in the circuits we've looked at here. Okay, so next what I'm going to do is talk about a major application of filters, and that's an AM receiver. Okay, so let me do radios 101 for 30 seconds. So these guys have an antenna. Okay, you take a ground here, and then so you pick up a signal at your antenna. Okay, there's an implied ground as well. And what you do as a first step is you begin processing the signal now. Okay, and what we place right there is a little filter that looks like this. It's an inductor and a capacitor in parallel. And this capacitor is really your tuner that you can tune to various frequencies. And then what you have here is a bunch of other processing and end up with the speaker. And the processing that happens here is you have a demodulator and you have a amplifier and a bunch of other things that let's not worry about them for now. Okay? And what we do here is the antenna picks up a signal. Okay, so in some sense, this part of the circuit here is your source. Okay, so I can replace it with its Thevenin equivalent. As follows. Okay, so the front end of your radio looks like a VI, R, an L, and a C. Okay, where have you seen this before? Right there. Okay, that's the front end of radios. And so let me tell you why I need a bandpass filter in a radio out here. So the way life works is as follows. So I have my frequency. Let me do this in not in radians, but in kilohertz for now. And let me plot your radio signal strength. So in the Boston area, the signals go between 540 kilohertz, and they go all the way to 1600. In some areas, we've begun using the 1700 extra band as well for some new stations. So this is the frequency range of interest. So if you look at your radio tuner, you'll see 540 kilohertz all the way up to 1600, and you can tune your AM radio. And the way it works is that each station is given 10 kilohertz of spectrum here. And so this is at 1,000 kilohertz, 1,010 kilohertz, and so on. And each station transmits its signal in plus or minus 5 hertz, 5 kilohertz around that point. And this station transmits it here. This station transmits it here, and so on. Okay? So this is 1030. Okay, this guy is WBZ. WBZ News Radio 1030, for those of you who listen to it. Okay, so what happens is that at 10 kilohertz, each station gets 10 kilohertz, and So WBZ transmits in the 10 kilohertz around 1030. Okay, so notice that each of these signals transmitted by radio stations happen within small bands. Okay? Now, you'll learn a lot more about modulation and how do you get a signal to go in a small band and all that stuff. You will learn about that in 6003. Okay, for now, don't worry about how I did all of this. Okay? So how do you listen to that station? The way you listen to that station is you put a low-pass filter here. You put a low-pass filter that does the following. Let's say I want to hear WBZ 1030. If I pass this entire signal through that filter, and if I arrange to have the omega naught of my filter at 1030, okay, if I can arrange to have the omega naught at 1030, then this is the response of my filter, and I'm going to pick out this guy and cut out everything else. Okay, I'm just going to get this. And that is... Let's listen to the station for some time.
This is WBUF. We interrupt this broadcast with a live update from our political desk. Arnold Schwarzenegger, the governor-elect of California, made a second. Expressing concern at the continuing bloodshed in Iraq, Schwarzenegger offered to lead a crack Grand Ops team into Iraq on a search and seize mission to apprehend Saddam. President Bush reluctantly took him up on the offer, which now leaves California -1 governor. Rumor has it that Eddie Murphy and Nick Nolte have both stepped up to the plate in the event of a re-election. And yes, California is in for yet another 48 hours. This is Sam Gallagher from WBUL.
Okay. So you can see I can tune to the station WBUL.